All right, so lesson 32, part 2 video. We're going to talk about the effect of concentration. So in order, hopefully you may not remember, but when we talked about standard reduction potential, so we had the E naught values, the concentration was one of the things we set. And so the equilibrium values for standard reduction potentials were either 1 molar or 1 atm. So when we have non-standard concentrations, we have to use a special equation which is called the Nernst equation. Okay, so this is when we have non-standard, meaning it's not 1 atmosphere, it's not 1 molar, it's something other than that. We use the Nernst equation. Okay, because it's non-standard, meaning not at equilibrium, we're going to see the reaction quotient, which we remember had the relationship Q is less than K, Q is greater than K, Q is equal to K. So it's going to allow us to tie something back to equilibrium. So we have some fill in the blanks here. During the operation of a galvanic cell, electrons flow. Hopefully you remember this is from left to right, which is anode to cathode, because the anode is oxidation, which is loss, and the cathode is reduction, which was gain. This will results in a decrease of the reactant concentration and an increase in the product formation. This results in an increase. What? Circle money? I don't have any circle money. My cabinets?
Yeah.
I don't have any money in my cabinets. I'm recording this lecture though, okay? In just a minute I'll help you. We're learning about coins at school, so he's looking for circle money. I know. So eventually, so the Q will begin to increase as it approaches the value of K, which will then cause the E value to decrease. Eventually, the cell will reach equilibrium. At equilibrium, E will equal 0. So it's going to go from positive to 0. And then it's going to be at equilibrium. And this is where Q is equal to K. So that's something that we have already learned, something that we are familiar with, hopefully, at this point. Okay, so consider, I guess let's see this in a practical sense. Consider the reaction of metallic copper with iron 3+ to give copper 2+ and iron 2+. Okay, so it's giving us the information. First, it wants to know what is the cell potential. So it's not asking about E cell naught. It's asking about this E value, which is non-standard conditions. E cell naught, with that little symbol up there, is standard reduction potentials. And that only is the value if the concentrations are 1 molar and 1 atmosphere. So we know that these concentrations are not 1 molar and they're not 1 atmosphere. So this is going to tell me I need to use the Nernst equation, okay? Because I'm calculating non-standard conditions. So the first thing I'm going to do is I'm going to write out all of the things that I'm looking for. Okay, so it wants to know what I'm looking for is what is this value right here. Okay, now this is going to come from a table, E cathode minus E anode. This is the number of electrons, and this is our products over reactants. So we know everything that we need. The first thing that you have to do though is we need to know what the balanced chemical equation is going to be. So I'm starting off, it says copper solid is going to go to copper 2+. It needs 2 electrons to be given up to do that. And iron 3+ is going to gain 1 electron to form iron 2+. So it's becoming less positive, therefore it's gaining an electron. Okay, so this is my oxidation, which is my cathode. This is my reduction, which is my anode. Okay, now if you remember, we need to take into account the differences in the number of electrons. So I'm going to multiply this by 2, which is going to then give me iron 3 plus 2 electrons plus 2 iron, 2 pluses. So 2 of everything. Now, if I'm going to add these two together, I can see my electrons are going to cancel out. And when I total them up, and I'm going to do something. I'm going to go ahead and add this information. And we'll see why that becomes important, or you may already be realizing why it's important, okay? Because it specifically says metallic copper. Well, metallic copper means solid. It is not, you cannot have a metal in an aqueous solution. You can have liquid metal like mercury, but it's still a pure liquid. So when we say it's pure copper, metallic copper, it means it's pure. All right, so this is my balanced equation. Now I need to look up my E naught values for my cathode and my anode. And remember, I'm going to pull them directly off the table. So you have a table right here. And sometimes, so I want to point this out. There are multiple versions. Like this is copper 2 plus and this is copper 2 plus. The difference is this is going to copper solid and this is going to copper 1 plus. So it's really easy to make a mistake to pull the wrong value because you don't look at what the product is, you're only looking at the reactant. So my value for copper 2 plus to copper solid is 0.34. That's a positive value. And iron 3, I'm going to expect that's probably going to be negative. Iron 3 to iron 2. Oop, I was wrong. It's actually more positive. Iron 3 to iron 2 by the loss of 1 electron is 0.77. So now you may be asking yourself, why? Oh, I sneeze. Oh my gosh, I'm so sorry. You may be asking yourself, why doesn't this 2 play into it? And remember, one of the rules we said back in lesson 30 at the very end was that changing the stoichiometric coefficients on the half cell does not affect the value of E. So even though there are twice as many electrons being transferred in this half cell reaction, it has no effect on the E cell or the E naught value. So we're not going to do anything to change that. So my E cell naught value is going to be 0.34 volts minus oh, wait. Okay, this is where I made a mistake. Okay, I knew I did something wrong. Okay. You keep your vowels together. A, O, and keep your consonants together. C and R. Okay, that's what went wrong. I knew. Well, okay, so this is oxidation, so it's losing its electron, which happens at the anode. This is reduction, which is the gain of the electron, which happens at the cathode. Okay. So if you may be asking yourself, why did you all of a sudden stop, or how did you know that that was going to be wrong? Well, I knew it was going to be wrong because I was going to get a negative E cell naught value. And everything we just talked about is that the E cell value should start positive and decrease to 0 as Q approaches K. So that's what alerted me to the fact that I had messed something up. The other thing that should have keyed it off was that I was looking for a more negative value because I had assigned it to the cathode when I should have been looking for a more positive value because it was actually should have been the anode, the flip-flopped. Okay, so there we go. Sometimes it helps to, well, I mean, I don't know if it helps y'all, but it helps to make a mistake so I can help you guys see if you make a same mistake, how you can catch yourself in the middle of a problem. Okay, so now I have my E cell knot value. So I have this. I know my number of electrons because I solved for that here. N is going to be equal to 2 electrons. So now I need Q. And this is where it pays off, if you remember, products over reactants. And so this is where copper being a solid becomes important, because it's not going to show up in the expression, because copper solid is equal to 1. Therefore, it doesn't show up in our Q expression. So now I'm going to plug in my values. My copper concentration when it's 2 plus is 0.25 molar. My iron concentration is 0.20 squared, molar squared. Remember, the units are going to cancel out. And then I'm going to divide that all by the concentration of iron 3 plus, which is a very small value, 1.0 times 10 to the negative fourth. So, and then that's going to be squared. So this will also become important because you can already see the product's concentrations are much higher than the reactant's concentrations. Okay. So when I solve for Q, I'm going to get a value. It's going to reduce down to 0.01 divided by 1.0 times 10 to the negative 8th. Okay? And that's going to be 36.0 times 10 to the positive 6. Okay? So now I have all of my values to plug in. .0257 divided by the 2 electrons times the value of Q, taking the natural log. So let's do this piece by piece. Make sure we don't make a mistake, or try to prevent making a mistake. So I'm going to solve for this first, and then I'm going to multiply that by the natural log of what came out to be about 1 million, and I'm chopping off some sig figs. So if you guys are leaving the entire number, you're going to get a different value. You might get a slightly different value, but it should be close enough. So then I'm going to multiply the 2 values on the right, because please excuse my dear Aunt Sally, is parentheses, exponents, multiplication, division, then addition and subtraction. 1775. And then when I take the difference between those values, it's a positive E cell value of 0.25 volts. And that suggests that it's spontaneous. Okay. So it's another thing about reporting the values. Usually you're only going to do 2, oh, that's so messy, 2 decimal places. Okay. Kind of similar to pH. You typically report to 2 decimal places. Okay. All right. So now let's solve this problem, and then we'll take another break. So this says to find the Q value at which the cell in problem 5 above becomes non-spontaneous. So what we're looking for is, if you remember, it's going to be when E cell is positive, it's going to go until it becomes 0, and that's at equilibrium. And then once it becomes negative, it's going to become non-spontaneous. So very similar to, if you remember the problem we did where we said, when does the reaction become non-spontaneous with our Gibbs free energy equation? We took the temperature, because we want to know what temperature at which it became non-spontaneous. We took the temperature and put it at 0. We're going to do the same thing here. We're going to see when E cell equals 0 volts. At that point, then it's going to become non-spontaneous. That's kind of like the tipping point. At that point, once it passes 0, it's going to become non-spontaneous. Now, these values aren't going to change, and that's nice because they are constants. So now I'm going to plug in my values to my Nernst equation. And I'm looking for Q. Oh, I should have. I got ahead of myself with some of the math. So now I'm going to subtract. And then to get rid of this, you need to divide it because they are multiplied by each other. And then I'm going to move this over here. So the positives, or the negatives, will cancel out. And this is going to leave me with a value of 33.463 is equal to the natural log of Q. And then remember, to undo log, you do 10 base. To do natural log, you do e. Raise it to the power of e. So e to the 33.463. And you should get a very large Q value of 3.41 times 10 to the 14. So that's the value of Q at which the equation becomes non-spontaneous in the forward direction and instead becomes spontaneous in the reverse direction. Okay? Okay, so concentration cells. Let's go ahead and we'll do concentration cells and then we will stop. So a concentration cell is going to use the same half reactions in both cells, so one oxidation and one reduction. The cell will function when the concentrations are different. So it's kind of like a concentration gradient. Nerve transmissions, so specifically like your sodium-potassium pump, operates by the same thing. It's by a concentration gradient across a membrane, and even though these concentration cells, like in a lab, don't necessarily have a membrane in the same sense that your cells do, they're going to have some sort of membrane which allows selective transport through. pH meters are considered concentration cells. The figure above is going to show a typical pH meter, so this should be above. And so as the concentration of H plus ions on the outside of the cell changes, it's going to determine how many are fluctuating into the pH meter, which then helps us measure pH. Either a large concentration of protons or a low concentration of protons will tell us the pH. Okay. So explain why the standard cell potential is always 0 for a concentration cell, meaning why is this value 0? And the reason why is, say that we have E cell naught is cathode minus anode. Well, if we remember back to the definition, it says it uses the same half cell reactions in both the cathode and the anode. So say, for instance, that it relied on this iron reaction. Well, we know that the E cell value, if we looked at the standard reduction potential value, is 0.447 volts. Well, if this half reaction is both the anode and the cathode, what that essentially means is that when I determine the E cell naught potential, well, it's equal to 0 because they cancel each other out. Okay. In a concentration cell, is the more dilute half cell the anode or the cathode? Explain your reasoning behind the reactions that take place. So if electrons are going to flow from anode to cathode, so we know this is left to right, and we're thinking about how electrons will respond to a concentration gradient. What this means, based on dilution, let's think about our cells. So if electrons are going to flow left to right, it means there must be less electrons over here on the right than on the left. What that means is that as far as the ions are concerned, that there must be, if this is going to be reduced and this is going to be oxidized, that this must be more dilute at the anode and more concentrated at the cathode. Okay, because the dilute is talking about this concentration right here of the solution. Okay, so more dilute at the anode, more concentrated at the cathode. Not about the electrons, but about their oxidizing and reducing species. Okay? So suppose that copper 2 plus is at this concentration on the left, and the concentration of copper 2 plus on the right is 1.0 molar. Label the diagram to show the anode, cathode, and electron flow, and then calculate the cell potential. So in this case, you have copper solid going to copper 2 plus 2 electrons, so it's what's being oxidized on the anode, and you have copper 2 plus 2 electrons going to copper solid as the cathode. This is where the concentration of copper is 0.01 molar. The concentration of copper 2 plus here is 1 molar. So over here, this is going to form more copper 2 plus, and this is going to form more copper solid. My dogs are barking at, I have no idea what. All right. Oh, and then electron flow is going to be this direction. Okay? And then it says calculate the cell potential. So what I'm looking for is this value right here. I know that E cell naught is going to be 0 volts. Number of electrons transferred is 2. My log of Q, it's going to be, if I add these two equations up, it's going to be, make them different colors. We'll do these in pink and do these in blue. So, okay, so that's them adding up. The two electrons cancel out. The cathode are in pink, the anode are in blue. Remember, the solids are not going to appear in our expression. Oh, too far. And so this is the value of 1 molar. This is the value of 0.01 molar. So now I'm going to plug my values into here where it's products divided by reactants. And so we're going to take 0.01 divided by 1, take the log of that, It's going to give me a value of -2. So now I can see my 2's will cancel out. My positives are going to cancel out, giving me an E cell value of 0.0592 volts, showing that it is spontaneous in the direction as written, where the electrons are flowing from left to right, from anode to anode. If you had made a mistake and labeled them incorrectly, like anode and cathode, you would have gotten an E cell value that was negative, which suggests you had them improperly labeled. And so the trick here is it's very similar, except for their concentrations are different. Okay, so I would say this lesson up so far is probably the hardest part of electrochemistry that we've done. So my plan is to post some additional videos like Khan Academy to help show you guys some extra examples of concentration cells and galvanic cells. The important thing here is that the galvanic cells are written with 1 molar and 1 atmosphere in mind. If you remember the cell line notation where it said you're going to use, you do the anode and then the phase, the line for the phase separation, and then you do the 2 lines for the salt bridge. And it said that if the concentrations are other than 1 molar or 1 atmosphere, you have to put them in there. So for concentration cells, if I was going to write the cell line notation, it would look something like this. Aqueous. Okay, where I'm showing that the concentrations, and I wrote the 1 molar in because I did on the right hand side. Technically, you don't have to write it in, but that's when those values become important. All right, we're going to finish up the lesson, part 3, with information about batteries, but I'm going to go ahead and take a break and then come back and talk about batteries.